Hello, everyone. So today we'll be reading a paper from NeurIPS 2020, and the presenter will be Pascal Klink, who is a PhD student at Technical University of Darmstadt. So you can share your screen and begin.
I'm currently, there we go, there's the presentation. So, where is it? Start, there we go. Okay, perfect. So, and now we can share it. All right, so I hope you can see the screen now.
Yeah, you can begin.
Yes, perfect. The only thing is, there we go, now it's gone. Yes, all right. So yeah, as Amin said, I want to present today like a paper that's called Efficient Model-Based RL through Optimistic Policy Search and Planning. And so yeah, let's get started right away. So what is this paper about? So this paper is mainly about model-based RL, which in turn is all about trying to boosting the efficiency of reinforcement learning by building a model of the environment in which it is acting. So I guess you all know this classical RL diagram where you have this environment and you have the agent, and the agent puts some actions into the environment and observes like a new state and a corresponding reward. And how you can conceptually think of model-based RL is basically as collecting this information about these state transitions in order to build a model about the environment you're acting in, and with that to more efficiently utilize this information. So, and this is kind of the setting that the authors investigated. And this algorithm box here is actually right away from the paper that they showed. And so what they are kind of thinking of is that you're using this data of the state action transitions to build what they are calling a calibrated dynamical model. I will come to that in a second, what exactly this corresponds to, but it's basically, you could think of it as a distribution over probability distributions, f tilde, where the function f is your actual dynamics function. And apart from that, they also assume that you know the reward function and you have a fixed horizon n. And in their particular paper, they looked at kind of a reduced setting where they had only one fixed initial state. But I think they argued in the paper somewhere that you can extend this analysis to multiple states, and they just picked it for convenience. So yeah, once you have all of these required inputs for their algorithm, what you basically iterate is you're using this distribution over your models, given the data that you have collected so far, and the known reward function in order to compute a policy for the current rollout. And after that, you then perform this actual rollout using this new policy and collect the new data and store it in your data set. And for some reason, I currently cannot see my mouse. This is why I'm having a hard time of actually highlighting anything. Wait, maybe if I'll try it. No, I mean, this is, wait. No, I still don't see anything. Okay, so I guess I won't be using pointers then for the presentation.
I guess you drew something. You drew something on the slide. Is it PowerPoint?
It's Keynote.
Oh, okay. So I don't know, but you drew something, a red point.
I drew something. Wow. I mean, I don't.
Yeah, just a point at the top of the.
I only see this. I only see the zoom overlay, so I can kind of on the zoom overlay, I can roughly estimate where my mouse is, but apart from that, I have no clue. But okay. Anyway, so let's try like this. So I will just like call out the names of the symbols, and this should work out as well. So, and during this rollout, as this little for loop in line 4 says. You have your true system function f, and the authors only also assume that you have like a noise model omega, which I think, yeah, they assume is zero, mean, and sub-Gaussian. I think the assumptions will also be there later again. So once you have this, the question is obviously how to design this function g that, given our current belief over the dynamics model and the reward function, gives us a new policy. And this is really kind of the main point of the whole paper. So what the authors argue, what you should not do, is basically this approach where you basically find this new policy by trying to maximize the expected performance over all the dynamics model, right? So you're taking this expectation over the dynamics model with respect to this function j, and this function j is basically the reinforcement learning objective. And yeah, I already said the authors argued that you should not do this, and this is in a sense interesting because this is what, for example, like I think it's a pretty well-known algorithm like Pilco, and there are also many other algorithms based on this idea to model-based RL that actually do this. And so it is a bit, in a sense, surprising that you should not do this. But the authors have a very good argument, because what they basically say is, okay, so they show, in a sense, for a special case of this RL objective, that this is not a good idea. And the special case is basically that you only have a horizon of time step 1. So basically you only do one transition and only get one reward. So that makes everything a bit easier to think about. And then they also just say, okay, our reward function is just the state. And for that, they assume the state is just a one-dimensional thing. And given that we then have this fixed initial state as 0, what you then basically see is that this RL objective J, it basically boils down to simply this formula where you want to maximize kind of this one-step transition. Basically, you want to maximize where you end up after one step. And if you then consequently do this, plug in this new RL objective into the above policy update, you basically get that you want to maximize the mean step that you take. And now this is really nice to interpret, because this is this is kind of a degenerate version of this upper confidence bound algorithm, which is a well-known bandit algorithm, where which kind of would look like this actually. So you also have this mean term, but you have this plus beta times and sigma S0A, where kind of this sigma is kind of the variance of your model. So you're not only looking at the mean, but you're also looking at the variance. And so basically this algorithm, oh, okay, this was not so smart. This algorithm where you just maximize the mean with respect to the action in the lower right of this slide right now, it's basically this UCB algorithm where you turn off beta completely. So where you set beta to 0. And this is known in the bandit literature to not be like a good approach to global optimization. And you see kind of here a visualization of this problem where you have this multimodal objective function. And on the left, you have this UCB algorithm with beta set to 0, which gets stuck in a local optima. And on the right, you have this beta set to 2, so kind of looking at 2 times standard deviation in a thing, what you can think of. And you see that this just works much nicer and actually does the job as you wanted. So, and this is basically the argument. So they say, given that we show it for this very reduced special case that it already doesn't work, we should not expect it to work like reasonably in an RL scenario, except for maybe random noise due to some initializations or rollouts and stuff. So after we now know that this is not a good idea, the question is, okay, what is a good idea? The next approach that they then introduce in their paper is also a well-known algorithm, also known kind of in the bandit literature, for example. And this is Thompson sampling, where kind of instead of looking at the expectation, before optimizing, you're sampling one model from your belief over dynamics models, and then you're optimizing the policy with respect to that. So it is known that this is kind of for, in this, we go back, in this setting, this Thompson sampling would also work. So this is also a well-known kind of result from this bandit literature. The authors at least say, and I will come to that point later again, that however, for example, for a general RL setting, sampling this one dynamics function from your belief over a possible dynamics function is infeasible in general, and that it's not so easy to do. And sure, in their experiments, we'll also see some advantage of their method over Thompson sampling. But kind of, yeah, they say this is in theory a reasonable thing to do, but there are some problems with it in practice. And so now comes actually their approach. And so what is the difference here? So you see that they now optimize over both the policy pi and the posterior dynamics model F tilde. So they do not sample as in Thompson sampling a dynamics model, but kind of they maximize also with respect to the dynamics model. So they want to kind of find the best dynamics model that is in this set MT, and MT kind of compromises all of the dynamics functions where which in a sense component wise are not too far away from the mean, right? So you see kind of that the absolute deviation from the mean is only allowed to be like beta times the standard deviation. So let's jump back. Yeah, okay. So if you think about kind of these plots here, right, where you have these uncertainty envelopes around the mean, basically you can think about of all the functions that would lie within this blue area, for example. And so basically you can select from any of these functions and yeah, choose this in a sense optimistically, right? So now an obvious question would be, okay, why should it be more easy to sample such a function f, to maximize over this function space f instead of sampling a function? And indeed, in general, this is also not feasible, but there is a much nicer way of implementing this objective approximately. And so what they are doing is actually pretty nice. So they transform this infeasible objective into a more feasible one by kind of creating additional control variables. And you see that these additional control variables are these AX. And you see basically that you take this extended dynamics model basically does the mean prediction. And then with this AX, you can then control basically you could then control kind of this uncertainty, which is represented by this covariance matrix sigma, to kind of shift the behavior around the mean. And the nice thing is obviously you can just take these extended actions into your regular action space that you use, for example, in planning, in order to just be able to keep reusing kind of slightly modified versions of regular reinforcement learning or optimal control algorithms. And in the appendix, the authors also have in general, this paper has quite a lengthy appendix, and they also have they also detail kind of variations of common algorithms like MPC or some RL algorithms and how to adjust them with this extended action space, basically. And so, yeah, this is really kind of the benefit of their formulation. And yeah, as I said, these AX are basically what they then call like these hallucinated actions. And the authors then continue to take a look at some theoretical guarantees. And they do this in terms of like bounding the regret of the learning algorithm. And the regret, for people which are maybe not so familiar with it, is kind of the loss that you accumulate over all the iterations up until time point t with respect to the optimal policy. And so the typical concept of these proofs is that if you can show that this regret grows in a way like grows sublinearly, so slower than a linear function, then you basically know that at some point in later iterations, you are getting closer and closer to the optimal performance. And so for this, and the authors will prove that kind of under certain assumptions, this algorithm has a sublinear regret, so kind of converges to the optimal policy. And so let's look at the assumptions that they put there. So this is the dynamics model that they assume, like, and which the learner does not know about. And so they have two assumptions on this. One is that this dynamics function f is Lipschitz continuous, and that the noise omega that occurs in each transition is sub-Gaussian. And what this basically means is that you have kind of, so it's zero mean, and then kind of the noise, it decays like in this exponential way that you know from a Gaussian with respect, I'm not exactly sure whether it's respect to some square distance or whether it can also be some other norms, but basically you don't want these heavy tails in a sense. This is kind of what you want. And so then, and now comes this, this idea of a well-calibrated dynamics model. So what you want is basically that for every state and action, that the true dynamics FSA is basically within the envelope of mu plus sigma times like a scale. And I think actually I did a mistake in this eta, because there should be like an additional scaling such that you can, for example, take 3 times sigma times eta instead of just 1 times sigma times eta. But basically what they assume is that if you again think about this uncertainty envelope around the mean, that your true function is always in this uncertainty envelope that you, for example, print when you are working with these Gaussian processes. And then they put a lot more Lipschitz continuity assumptions on all of the other parts. Basically, you want that the mean function of your posterior over dynamics function and the covariance function are Lipschitz continuous, and you want that your reward and all your policies are always Lipschitz continuous. And with all that in place, they can then prove this main theorem of their paper, that basically that this regret RT grows, if you look in this bound, you should, I mean, sure, there are constants and multipliers and everything, but the important thing is you have this t, and you see it's square root t. So far it's looking good that it's sublinear, because linear dependency on t then there would need to be a t somewhere. However, there's one term which is crucial, and that is this IT. And so the thing with this IT is basically this kind of tells you how fast the uncertainty of your function approximator decays as it kind of gains more and more data. And in general, it is very hard to bound this for general function approximators such as neural networks or Gaussian processes. But what the authors can show is that for Gaussian processes, this function IT is again sublinear in T. And with that, they kind of then ultimately can show that, assuming you're using Gaussian processes and these Lipschitz continuity assumptions and everything are fulfilled, that this algorithm then would kind of produce the optimal policy after a given time. Obviously, another implicit assumption is that this maximization, so computing the next policy, kind of always will give you the optimal policy given your current belief over your dynamics model. And I mean, if you think about that, these like policy optimization steps in model-based RL are typically implemented using, for example, just some RL algorithm or like some MPC style algorithms. This is obviously not guaranteed. They could still get stuck in a local optima. But yeah, so far through the theoretical guarantees. And now the bit more interesting part, I would say, and this is the experiments where they first did an experiment on an inverted pendulum swing up task. And the interesting thing here is that they kind of do this ablation in a sense over the action penalties. And you see, if there are no action penalties, you have the methods performing fairly well. And maybe I should explain a little bit more the x-axis. So they actually, for this experiment, they used 3 different dynamics models. So DE refers to a deterministic ensemble of neural networks. That means you basically, in order to capture a bit uncertainty about your function, you take, for example, 10 neural networks and train them on bootstrap samples of your data. You then have also a probabilistic ensemble of neural networks, where you have the same ensembling idea, but now each neural network produces not only a single output, but it produces, for example, a mean and a variance prediction. So basically predicting kind of parameters of a normal distribution. And then GP is then Gaussian process models. And you see that for no action penalties, the methods seem to work fairly well, although like the Thompson sampling on the GP, which is a bit interesting. And actually, this is something that I've looked into a bit deeper, which we can come to in a second. And you see that basically the more the action penalties grow, the worse the other methods are getting. And probably, and the authors argue, because they get like stuck in local optima because of the action penalties and just this sparse reward when getting up to the top, while their method is still able to find this optimal reward. And I guess like it's pretty intuitive, right? I mean, if you're able kind of to adapt, given your uncertainty, the dynamics in the way that will bring you to the high reward area, I mean, it's fairly clear that you will just always keep trying to use other uncertainty ways of getting to your target until you kind of find the way which actually like coincides with the true dynamics that you're working with. And so then they also did quite some other experiments. So for example, they had, I think it's this 2-dimensional reacher task where you kind of can think about the elbow, which you move in a planar space, both for sparse and non-sparse versions of the tasks. And you see again, I think here in these experiments, they always used either, I think, probabilistic ensembles or deterministic ensembles, but definitely ensembles and not GPs anymore. And you see, for example, for the reacher task, which is kind of the left column, you see kind of how sparsity in combination with an increasing action penalty creates problems for the other algorithms, but not for their method. And a similar picture is for the pusher and the half cheater task. Basically, like with increasing action penalties, the benefit of this of their method kind of becomes more and more pronounced. So this is kind of the part of the main paper. And now what I want to come to is a bit of criticism, particularly with respect to this first experiment where the Thompson sampling on the GPs did not really work so well. So, so for these probabilistic or deterministic neural network ensembles, this idea of implementing Thompson sampling is like fairly intuitive. So what they do before they optimize a policy in each route, they sample kind of the index of one neural network, assuming now they have, for example, K neural networks. So they draw from the categorical. And then they just fix kind of this neural network for the whole optimization. And so what I was asking myself, okay, how did they do it for GPs? Because in the appendix, they weren't so clear about it. And so this is why I took a quick look at the code. And in the code, I then first of all, they have really nice code base. So this is actually, I think, something very rare given typical scientific or paper code bases. So if you're interested in this topic, I think it's really worth checking it out. And so kind of for the Thompson sampling, they had kind of this abstraction that these are kind of the two methods with which you kind of tell the different dynamics models that they investigated, so that they should use now this Thompson sampling idea. And yeah, as I said, they have a nice code base, so kind of they nicely abstract the different dynamics models, and then obviously have these two classes, these two functions that are called in the main code. But the thing is basically for the exact or sparse GP models that they have in their code base, this was not implemented at all, basically. And so this is why I have the strong feeling that the Thompson sampling, it just did just sample randomly kind of from the GP in each transition. But this is not really what Thompson sampling would look like, because with Thompson sampling, right, I mean, what you would think of that you sample one function and then you kind of get coherent results according to this function. But if you just randomly sample from the GP, at each time, you don't have this coherency. And so I think what the authors should have done is, during this optimization, they should have stored the old transitions that have occurred so far in the rollout or in the policy optimization, and increasingly condition the GP on these old transitions to get kind of this coherent behavior. And yeah, so this would be really interesting to see how kind of this method, which in my opinion is more closely to Thompson sampling, would have performed. Yes, I think this is so far then it from my side. So, and now I'm seeing my mouse pointer again. Very nice. So yeah, if you have questions, I also have some other stuff, what particularly got me interested in the paper. So I don't know, when you're interested or want to know about this, we can also chat about this, but I think I already filled the half hour very well. So for now, let's see whether you have some ideas or thoughts.
Yeah, thank you very much, Pascal. So are there any questions or comments?
Hi, I have a question. In this paper, in the beginning part, they mentioned the two kinds of uncertainty. So this it says Gaussian process can differentiate these two kinds of uncertainty very well naturally. But I don't know how they control how they employ this how they control this uncertainty very well in their exploration policy.
Yes, so I mean, I think a good thing to visualize this is this part basically. So here you see, for example, in the can you see actually my mouse now?
Yes, we can.
Okay, so right here you have basically the three data samples, and in this area here you basically see kind of this uncertainty envelope is kind of very large, right? And so this is kind of basically this epistemic uncertainty, which basically corresponds to I am uncertain because I haven't observed anything in this area. And you see that like here, right, although you have basically, you have data points, there is still some uncertainty left. And this is then kind of this aleatoric uncertainty, where basically you say, okay, I have observed data, but kind of the data in a sense like gives me the feeling that there is still some noise which is inherent to the system. And this is kind of this this thing that you have in GPs and which you can nicely kind of dissect for Gaussian process models, basically, or Gaussian process regression models. And yes.
Yes, thanks. It makes sense. And another is how this is used in their exploration policy. Yeah, you see, yeah, basically.
Yes. I mean, what they basically say, I mean, kind of this idea of aleatoric or this well distinguishing between epistemic and aleatoric uncertainty really is in kind of this idea of having a calibrated dynamics model, where you basically want that the true function, right, is basically, think about this thing, right? This thingy here is kind of really this blue envelope, like in this plot. So basically what you want that your true function kind of is always within this blue area. And what you then kind of also want for, if you have like such a good dynamics or yeah, a well-calibrated model, or yeah, like let's say a useful model, is that if you observe data, right, that this envelope kind of shrinks, because that kind of means that you always can very well kind of estimate what is a behavior that I can expect from the function that is kind of plausible given the data that I have. So this is kind of the thing that they want when they say, okay, we want models that are well calibrated, that then can nicely distinguish aleatoric and epistemic uncertainty in these things. And I agree that, for example, for probabilistic and deterministic ensembles, and the authors also state that in a sense by saying you cannot bound kind of, right, because the authors, if you look at the proof, right, so basically the combination of this well-calibrated model here and this yeah, complexity measure, which really kind of says intuitively how fast is my variance, my uncertainty shrinking if I observe data, kind of they say that, for example, this thing you cannot really bound for a neural network ensemble. And so yeah, this is kind of why for these ensembles, obviously, at least from a theoretical side, it's much harder to really guarantee that they reasonably like express epistemic and aleatoric uncertainty.
Okay, great, thanks.
Okay, is there any other questions from the audience?
Hello.
Hi, I just want to ask a very simple question. Is this like a variant of like UCB, but for the model and for the policy at the same time?
Yeah, I mean, if we look kind of, yeah, wait, where do I have the UCB? Okay, I have it overlaid, so let's go here. Yeah, yeah, it's a good question. I mean, it's definitely related, right? Because kind of like this additional maximization, right? That you like maximizing this function, you can only really kind of get a lever on this additional maximization over the dynamics function in areas where your model is uncertain, right? So it is definitely related to the UCB algorithm, I would say, yes. But it's, I can't really, I cannot wrap my head around how exactly they would differ in behavior in a sense, right? Because I mean, I guess actually that you have a more fine-grained control, right? Because yeah, actually, wait, okay, I don't see my mouse again, so let's just move this one. So, and now I can finally draw, which makes things much nicer. I mean, right, so here basically what you would do is you would have these eta variables and you would basically multiply these eta thingies towards this. And this is, I mean, in a single step, I think, like, which I think UCB originally originated from, like in these bandit settings, this may not be so interesting, but in a multi-step setting where you have dynamics, right, you may actually not always just want to add like this this constant or like this fixed term here to your mean dynamics, but you may want to be able to more flexibly shift kind of the behavior of the function. And so this is, I think, why it's actually a very reasonable extension of this UCB setting when you're actually not expressing the optimism with, because I mean the UCB algorithm, right? I mean, there you typically in this bandit scenario, you model kind of the expected return or the return of this arm. So you're modeling kind of a reward function, but what they are modeling with the is kind of a dynamics function, right? So I guess this is probably the key difference why you now want to have this additional control variables eta instead of just always taking kind of the maximum, because I mean, there is no intuition of what is a maximum of a dynamics function in a sense, right? Because in a dynamics function, you don't know that larger is better, which you kind of know if you model this as the reward. So this is probably actually the key reason why you want this.
Ah, okay, I understand what you mean. But then,
Yes.
what is this eta here? Okay, so
yes.
yeah.
Wait, let's go back to the here. So I mean, the eta is basically here this ax. Sorry, I mean, I think in their paper they used this eta, so I should have written ax, right? So here you have this kind of thing, and as opposed like in the upper confidence bound, right, you would basically always just do this. So you wouldn't have these extra terms and you would fix this. And while this is kind of reasonable for a reward function where kind of, you know, okay, a higher reward is better, so I should try this one out. A dynamics function, I mean, because I mean, it's just a very different thing. So you don't know whether you always just want the maximum response of the dynamics model. Maybe you want exactly the opposite, so the minimum response. And this is what you can kind of control with this extended control input in a sense. Does this make sense?
But here still we always want to get the argmax. So even we
yes. But yeah, maybe it becomes clearer. I mean, because the thing is, yes, we want to get the argmax, but the thing is our function f, like this fx, okay, I cannot really write, so let's just keep it, let's just write it with f. So but this function f, right, it just gives us the next state, and then we are plugging this into r s, and then, yeah, I mean, assuming we take another action in the next state. And the thing is, like in typical UCB applications, right, you model this function, so you model the reward function in a sense, and in their algorithm, they actually model the dynamics function. And I think this is why in UCB, you don't really need these additional inputs here, because with the reward function, you always just want larger is better. But the thing is, who says that like you should always take the maximum response of this dynamics model, right? Because maybe your reward wants to go like exactly in the, how to say, in the minimum direction in order to make the reward large.
I understand what you mean here.
And this is, I think, why they need, or why they really want this here.
Yeah. I mean, yeah, I mean, but there's still, yeah. So For the reward, if we want to optimize the reward, what we want is always maximize the reward, and we get the upper bound for the mean with the upper bound. So the upper bound is the confidence, how confident we are at the current time step.
The difference,
but,
yes, yeah. And I really think,
yeah.
No, sorry, yeah.
But for the model of the environment, we still want to estimate. We have the mean, and also we need to control how likely the uncertainty of the model. And I think
exactly.
Yeah. So
and the thing is, it's just kind of, it just differs how you in UCB you exploit the uncertainty by saying, well, if I don't know if my reward is not good in this area, I just assume the highest that I can reasonably assume to get. Whereas if you now, like in the RL setting, model the dynamics function, you just need to exploit this uncertainty in a different way by not just saying I always want the maximum response of my dynamics functions, but by saying I want the response of my dynamics function that leads me to the highest reward states, basically. And so, right, this does not need to mean that kind of, I mean, what in a sense UCB would do, right, is kind of, it would kind of always, like, it would have kind of this objective function at like at the current iteration here. But the thing is, kind of what you would want with their algorithm is, for example, that you kind of would, for example, want to sample a function that kind of, I don't know, does something like this, right? So that goes like maybe something like this. And but this behavior, like for the dynamics function, may still be optimal because it gets you to high reward states.
Yeah.
And so this is really the difference, how you're exploiting this uncertainty here because of the difference of the functions that you're modeling.
But how they say in the paper, I saw here, like they combine off policy with online planning. How is that possible?
Oh, I think if I understood this correctly, they were doing some, I think they used maximum MPO. I think this is this maximum a posteriori policy optimization, if I'm not mistaken. But basically they use an RL algorithm to get kind of a baseline policy. And then during rollouts, I think they use some MPC method in order to further improve the performance given the baseline policy. Like similar to, you can think of it, I mean, I know Tuan that you work with it, like, for example, like, I don't know, AlphaGo or whatever, right?
Yeah.
Where you kind of have your lookup tree in order to boost kind of the performance of the policy that you have once more, in a sense. I think they did something very similar in their experiments.
Yeah, I mean, so in AlphaZero, we have the current estimation of the policy and the value. We build the tree. We got the
exactly. Basically, think about this in a continuous way.
Yeah, it should be offline policy, yes. So that we can combine with online to improve it.
But yeah, I mean, they didn't stress so much about what, I mean, sure, in practice, I guess this is a very important aspect of RL, but they didn't stress so much about what they exactly use for computing the policies, at least not in the main paper. Yeah, they just said, okay, we just like have some method that computes kind of this new policy given the dynamics model, kind of in an abstract sense. But yeah, I definitely agree that this is important in practice.
Yeah, this is very nice work. Maybe I need to read it. Thanks.
Yeah, sure.
Hi.
Hey.
I have some thoughts that, as you mentioned in there about this Gaussian process, that they didn't consider.
Ah, yes.
Yes. So one thing could be that, because if we want to use this sparse Gaussian process, then it can be like a the order of n cube, and it can increase the computational time as well. So
yes, that's true.
And the implementations of like the straight implementation of GP is not there at that time, I think, in Python very well. Like there are like some libraries like Pyro and PyGP, but they are not straightforward to get.
Yes, although I mean the thing is, right, I mean the main, I mean a big computational burden is kind of tuning GP parameters, right, the hyperparameters, because this is kind of the iterative thing that you then need to do. But I mean, you could kind of optimize the hyperparameters on the fixed data set, right? And then you could just like keep these hyperparameters fixed during the rollouts. And I mean, then you could use some pretty, I mean, there are kind of update schemes which are scaling. I mean, we discussed this in I think Riza, yeah, you're still here, right, Riza? Yeah. So yes. Yeah, we discussed this. I think it's ON, and then there are even approximate versions, because I think that's a paper that you shared, which is even constant in terms of updating a GP with fixed parameters when you get just a new data point, basically.
Yes, that was the idea of the paper. We haven't tested it, so we don't know the limits to it. But it's possible.
Yes, so this would basically be the idea, to use kind of this in order to, right, you have your actual data set of data that you observed, and then you start kind of the optimization, and each transition that you simulate during the optimization, you add to your data point, to your data set, because then you would kind of converge more and more on one deterministic function. And I mean, I don't know if this exactly corresponds to Thompson sampling. I'm not like, I didn't do any proofs or whatever, but it's definitely closer to Thompson sampling, that I would say, than just like always just sampling from the posterior distribution that you have given your data set at iteration t, right? Because then you're ultimately still averaging over all different functions. So it's not a real Thompson sampling, I would say. Or at least it's less of a Thompson sampling than the thing that I just sketched out.
Right. I will send the paper in the chat just for reference. Okay.
Okay. Thanks. Yeah, I think they're quite interesting, but there are like many challenges.
Yes, I mean, it's not easy, and I mean, I guess you cannot blame them for that. I mean, because yeah, I mean, there is no like real, like, or I guess, or at least I don't know a real analog where people say, yeah, this is how you do Thompson sampling in an RL setting with a GP model or something, right? So I guess, yeah, you cannot blame them for not coming up with a new method to that as well. It's just something that I realized because I was just really surprised that like it didn't work, like even in the non-constrained setting where, no, it's correct. Yeah, the Thompson sampling here is low, exactly, and just the greedy, and yeah, is actually working. Yeah. Or actually, oh wait, I'm currently thinking whether I misread these things and they didn't even perform these experiments. This is actually a good. They didn't perform it?
Yeah.
Oh, yeah, okay. So then, okay. So maybe then, okay. I mean, okay, at least then they don't have like this result in there. But I mean, it would still be interesting to see how it actually looks like. So they didn't even perform this thing. Okay. I see.
Yeah, like details of the papers are sometimes hidden in the.
Yes, I mean, their appendix, I don't know, it was like, I mean, sure, they have also proofs, so this is pretty verbose, but they have also a ton of ablations in the appendix. I don't know, I didn't check, I guess, I mean, it was a NeurIPS paper, so I guess they have a lot. I think the reviewer discussion is also public for NeurIPS papers. So but I didn't check whether this very extensive additional evaluations were because of some reviewer discussions or what was the reason for that. But yeah, I mean, it's a, like, I think 40-page appendix or something. It's really large. Yeah.
Yeah, okay. great. It was a really nice discussion. Yes, thank you.
Yeah.
Thanks.
Thank you. Thank you, everyone. And thank you, Pascal, again for the great presentation. So if there are no more questions, I guess we can wrap up the meeting then. Yeah. Okay.
Thanks for the presentation.
Cool. Yeah, no problem.
Thanks. Yeah.
Thank you. And have a nice weekend, everyone. Bye-bye.
Yeah.
Bye.
Thank you. Bye.